And what is this stuff, dark matter and dark energy, we always talk about? Now, I'm not going to answer these questions today. These are the questions for the future. And that's what I love about astronomy, is our future is the future, it's not the past. To understand the future, we need to understand the past. When I arrived in Australia in 1994, there were exactly 0 exoplanets known. This is the list today, 1,935 planets in this area explode. I'm doing my little bit at Mount Stromlo with Australia. These 2 of the last 4 we've helped discover, but it's a tip of the iceberg of some of the things that we're going to talk about. To understand how we find planets, let's think a little bit about physics. Every atom has a fingerprint of light. And that fingerprint of light we spread out into a spectrum, the colors of the rainbow. And we do that, we can identify what, for example, the sun is made out of. And it turns out the sun is made up of every single stable element that we know of. And so we can identify that with those very precise measurements of color. And those very precise measurements of colors do not just tell us what the stars are made out of, but they can also tell us the motions of stars. So, for example, when the Earth goes around the Sun, the Earth goes around 30 kilometers per second, so very quickly around the Sun. The Sun, which is 1 million times more massive, does a little circle, 1 million times slower. And so, due to the Doppler shift, the light, those colors shift back and forth, red and blue. Red going away, blue coming towards. And with current equipment here in Australia and around the world, here is a spectrograph on the AAT up near Coonabarabran, we are able to measure the velocities of distant stars at the rate of about 0.5 meter per second. This is about 0.5 meter per second. Imagine we can be looking things trillions upon trillions of kilometers away, and we can measure walking speed. We're probably getting to the point where we can even do sort of, this fast. That's about where the limit starts creeping in. So we have this amazing technology to find planets. But it's not the only way we find planets. Another way we find planets is the way that Australia was essentially the thing that pointed towards Australia being explored by Captain Cook. The transit of Venus. A planet goes in front of a sun. And when it does it dims the star by a small amount. 1 part in 10,000. But with modern telescopes in space and on the ground, we're able to look for those tiny little divots. The Kepler telescope has been working on this project for the last 5 years or so, and has found a remarkable number of planets. Thousands. Here's what it's found thus far, just announced in the last few days. Here we plot how long it takes, what the year is, 1 day to 1,000 days, remembering Earth's 365, and the radius relative to Earth. Now, this doesn't show what the star is that the planet is orbiting, but they announced Earth 2.0 a few days ago. A star down here, 385 days, that was just a little bigger than Earth. Prime real estate, possibly for humanity. But can we go through and learn about those stars? And the answer is yes, we can, because we're going to discover a lot of them using more sophisticated satellites over the next 5 to 10 years. They're going to find bright nearby Earth-like planets. And then with the next generation of telescopes, we're going to be able to essentially do an experiment. This is Venus in front of our sun. It's not been photoshopped. It's a real picture. Look at the rim. There's a little white light color. That's light refracting through the atmosphere of Venus. When it does that, it picks up the fingerprint of what's in Venus's atmosphere. That we're going to be able to do for Earth-like planets around nearby stars. And when we do that, who knows what we're going to see? But we might see, for example, oxygen. Why is oxygen important? Well, oxygen is the stuff of life, literally. The reason why our atmosphere is about 20% oxygen is because life made the oxygen. Our planet would not have the oxygen in large quantities without life. And of course, there are other signatures. This experiment is going to happen in the near future because we're building the next generation of telescopes. Australia's partners in the giant Magellan telescope, a telescope 25 meters across. The Europeans are building a 40-meter telescope, a 39-meter telescope. These new facilities are going to have the power to look for the signatures of life around nearby planets. All right, so what's the life history of the universe? Question number 2. Well, I need to go through a little bit of background here. In 1929, Edwin Hubble became a very famous person when he did this diagram. This diagram plotted for galaxies how bright their stars were. Fainter stars meant a long ways away. And their redshift measured from the Doppler shift, or at least he thought it was the Doppler shift. Turns out it was the expansion of space, as I'll show you. And he saw that the further an object was, the faster it was moving. And from that, he announced to the world in 1929, the universe is expanding. Why did he say that? Well, let's do a little cartoon of the universe. And I should say, Swinburne has done almost all of these animations. We work very collaboratively here in Australia, and I'm giving talks around the world, and I essentially use everything from Swinburne. So thank you very much, Matthew, for the group. So, Hubble's law. I've just expanded the universe. Now let's overlay before and after. What do we see? We see nearby objects have moved a little bit. Distant objects have moved a lot. The further away as you've expanded the universe, the more the motion. Just what Hubble saw. And when the universe is expanding, it doesn't matter where you are. Everyone in the universe sees the same thing. The further away, the more the motion. Okay. So, when I arrived in Australia in 1994, we did an experiment. We looked at that expansion like Hubble did, but we looked back in time. We looked back billions of years. So we compared how fast the universe was expanding in the past to the present. And what we expected was that the universe would be slowing down, and the heavier the universe is, the more the gravity, the more the slowing down. Easy experiment. Except for when we did the experiment, we got the wrong answer, as I'll show you. One thing to think about is when the universe is expanding, it has an inevitable beginning. A beginning that is the Big Bang. If things are expanding, that means in the past they were closer. And further in the past, closer and closer and closer. There is an inevitability of the Big Bang if the universe is expanding. And when the universe is smaller, it's hotter and it's denser. So, if we go back and use a telescope to look back in time to a small piece of sky, much smaller than the moon, we are looking back in this image 13 billion years. Many of the people here at Swinburne are some of the leaders in understanding this part of the universe. And so you're looking back to galaxies that occurred way before the Earth was formed. So this is the childhood of the universe. We sort of understand that. But if we go before, there was a time when this is what the universe looked like. And if you can't see anything there, that's because you can't see anything. The universe had a beginning. Before this, we can see it, it turns out. It was hot, so hot, it was glowing like the sun. So this is an image when the universe was a mere 380,000 years old. It was nearly 3,000 degrees, hot, glowing like the sun. But we can go back before this. We can look to a time when the universe was 100 million degrees, only a few seconds old. And we can calculate the nuclear reactions because the entire universe is a giant nuclear reactor. And when you calculate out how much hydrogen, helium, deuterium, lithium there is, you get exactly the answer of what we see in the primitive parts of the universe. So that's the way we trace back to a second. So the universe was born with hydrogen and helium, but not the stuff we're made out of. No carbon, no oxygen, no iron in the chairs that you're sitting in. So, with new technology, the James Webb Space Telescope, we're going to be able to look back. We're going to be able to look back to the first stars and galaxies. It will have the power to see literally the birth of the universe. We'll also be able to use the giant telescopes that we have access complementarily with that new space facility. But I have to admit, I myself am impatient. So we have a fossil record of that time of the universe here, and Australia is one of the leaders in the field of galactic archaeology. The problem is there's 100 billion stars to choose from, and a few of them are the first ones. So we have been, as a community, build a new facility. SkyMapper has the largest digital camera in Australia, at least one that's not classified. And we can go out and we can do a census of every one of those stars. And when we do this, we can judge how hot they are, how far away they are, and what they're made out of. And one of the objects that we have found is the most primitive star. A star, and here's the fingerprint of iron. This star has no iron whatsoever. It's the only star that's been discovered that has no iron. Now, it does have calcium, it does have carbon, it does have small amounts of magnesium. We think this star was created from the ashes of one of the first stars. And so, we're at the beginning of this, we hope to find a lot of these. A story yet to unfold. Now, I told you that this is what the universe looked like when it was 10 million years old. I lied. That's what it looks like to us. But if you have optical, that's through optical eyes. If you have radio vision, we think it looked like that. Why? Because cold hydrogen emits a radio wave. And it turns out that atoms with their protons and electrons have spin, and when they disalign, you get a little radio wave that comes out at 1.4 gigahertz. So, we can go through and we can, if you're on the right site, 1.4 gigahertz turns out to be, by the time it gets to the Earth, right in the middle of the FM radio band. And so we can go to a place that literally has no FM radio stations. The far west, whatever, I'm going to mess it up now. Anyway, so this is the Murchison Wide Field Array that Australia, many of the universities and CSIRO are building, and we can see this new capability to look back to that era where we can see the hydrogen that's left over from the Big Bang. And that hydrogen, when it's cold, emits radio waves. When it starts getting heated up by stars, then it disappears. And so we'll see a universe go from being a piece of cheddar to a piece of Swiss cheese, and eventually you won't see that hydrogen at all. Of course, this is a precursor to what we hope will be a magnificent multi-billion-dollar international facility, the Square Kilometer Array. So, what is the stuff we call dark matter and dark energy? Well, I'm not going to give you an answer on this stuff, but what's dark matter and dark energy? This is the experiment I told you of earlier, where we look back in the past and we compare distances and expansion from the past to the present. So these are on this side, the present, and then the past. And what we see here is that the universe was expanding slower in the past than it sped up. And that indicates that gravity is pushing rather than pulling. Einstein gave us what we need. He called it cosmological constant. We call it dark energy. Energy that's part of space makes gravity push rather than pull. But we need a lot of it. Now, we can also go out and measure the universe using, for example, maps that we've done here in Australia of the universe. And we can measure how much gravity there is. We can go to the early universe, to that picture when the universe was hot. And that universe there is a picture right after the Big Bang. We're seeing sound waves splash around the universe. And when you, for example, throw a rock into a pond, then the splash marks, well, they depend on what the pond's made out of. And so we can actually see what the universe is made up of with this experiment. Turns out the Big Bang threw a bunch of gravel into the universe. We see the waves shimmer around, and then we look at what the universe looks like compared to our physical models. And you get an amazingly precise answer. we put this all together, what do we find? Well, we find the universe is 5% the stuff we're made out of, atoms. 95% dark energy, dark matter. And it's from all of these experiments. So what's dark matter? Well, you don't really know. We think it has gravity, just like atoms, but it's invisible because it can pass right through itself and everything else. It's probably passing through us right now. So, in this very famous image called the bullet cluster, we can actually see two big clumps of galaxies crash through each other. The atoms collide, get left of the center, and the dark matter, which we can see from its gravity, goes right through, just as expected. So, I don't know what this is going to be, but we're trying many ways. We might be able to, if it's a particle, create it in the Large Hadron Collider. We might be able to detect it in a mine. For example, we're putting an experiment in Victoria. Or it might sometimes collide with itself and create an astrophysical signal. These are experiments that are happening now that we hope will tell us what dark matter is. Dark energy? Well, the only tool we can do is really see what the universe is doing back in time. So Australia is using its facilities and working with a facility in Chile to map back the expansion in time. Here in Swinburne, you guys have led an experiment to take the sound waves and map them out in the galaxies of today. These allow us to make much more precise measurements of what the universe is doing in time. And so the question is, does dark energy get created exactly as space is created as the universe expands? And that means, is it accelerating the universe as Einstein suggested it would? At this point, Einstein seems right, but time will tell. There are huge experiments being done right now. So what's our future? Well, our sun's nuclear reactor is getting stronger and stronger. And in about 500 million years, it's not going to be very pleasant to live on Earth because it's going to be too hot. This is the serious form of global warming, not 5 to 10 degrees. This is 50 degrees. So our future is doomed. That's why it's good for us astronomers to be out finding the next place to go. But compared to our sun, the actual future of the universe is maybe even more dire. Why? Because dark energy dominates the universe. And the more the universe expands, the more dark energy dominates the universe. And eventually, the universe will be expanding faster than light. Eventually, the universe will be expanding even faster than light can travel through it. Meaning, as light tries to travel from different parts of the universe in the future, it won't get to us. We will look out and we will see a universe of darkness, no galaxies. Our own galaxy will stay put. That's another talk. We won't talk about that today. But the rest of the universe, that really interesting part, that disappears. We become the world's most boring place. So unless that dark energy somehow disappears, the universe will expand at an ever-increasing rate and fade away, meaning that myself and my colleagues here at Swinburne will be unemployed. Thank you very much.